talk about from the nucleus and the wave?
Wave would be length.
Okay, yeah, okay. And for the nucleus?
Diameter.
Diameter, which in the end is length as well, right? Actually, so that's why this will be very important
Simple stuff
because
I've
there are many
already
other
been
waves
through.
which gives us very good information
Excuse
about
me.
what happens in some
How
parts,
could you do
galaxies,
that?
planets, stars, etc. They are not just well stars which have been, so they or which will form. They are not stars.
Higher the frequency.
Yeah, exactly. Huh? Yeah, that's always a good thing to think about, right? And 2 centimeters is obviously already comparatively short. Visible light, like you said, is interestingly much shorter, but hence much lower frequency. Huh? Okay, and it gives us the actually because this is a superposition question ultimately. But nevertheless, what does monochromatic mean?
Only one light, one color light.
Okay, so is natural light monochromatic?
Jala. No. Jala.
Right, exactly. What could be something we still see as a visible light but monochromatic? What would that typically be? Can you think of one?
Part of a rainbow.
Okay, yeah, that's an interesting one. When you think of, think of kind of, well, for us at least on Earth, artificially generated light. Of course, in the universe, we can see that as well anyway. But, and it's a standard feature in any science fiction movie, basically. What type of ray would that be? Which we can still see, but is monochromatic. With the trigonometric values, if you want to say so, for cos and sine. Because it's a common one that very often students say for 45 half. Somehow, because 45 is between 0 and 90, so it's understandable, but it's not. However, sine and cosine, of course, are the same because they are in the half of 90 degrees, so halfway through between 0 and 90, but that doesn't make the cos or the sine half. Unless you already said, of course, the square. Sorry, maybe did you mean the square or the cos only?
The square. That's so boring, man.
So, and actually, this is now the we don't know because it just first exactly. So the two, 1 and 2 are identical. Then it cannot be something which is polarizing, right? Because it clearly says it's a polarizer. So the polarizer will do something with the incident on the polarizer with the vertical transmission axis. So that means clearly it will henceforth pass through, but in a changed value. And at the end, it's still the same value. So we must say, well, the second part is either a port one with a vertical transmission axis, or it's non-polarizing glass, like you said. And hence, where we can come up with C. Huh? Okay, so it's a bit more a puzzle than anything else. Let me see. Yeah, maybe 3. And then we go to the theory part because this is well, it's not so important anymore because hardly anybody listens to a portable radio. That's more or less gone. But not everywhere is internet, and the radio stations, not all of them, they still transmit radio waves. A lot of them have changed to internet broadcasting actually. But you know a portable radio, right? I mean, sorry when I ask, but better ask than not. So it's just that thing there. It's the loudspeaker, It has some knob here, and of course it has an antenna, which is extended. Yeah, the superposition wave compared to gravel, compared to sand, something like that.
Oh shit. Ah, whatever, I fell off. Okay. Nice.
Hello, Christopher.
Hello?
Hey, how are you? How are you?
I'm fine.
Okay, all right. That's a bit strange with the connection. Huh? Okay, so let's just go into it, and we continue with our superposition. Do a couple, still um, some theory actually, because it continues, but we have a couple of questions, of course, as well. Huh? Then starting. Okay, so just briefly go back. We looked at the, well, how we can add the waves, the superposition, of course. Now we continue with that a bit by talking about, like we had it mentioned, superposition, um, sorry, constructive or destructive interference, so to speak. Huh? So either they, like here, we see, like what I mentioned last time, the ANC, the advanced or automatic noise cancelling, when obviously the waves cancel each other at any given time, because either it's negative or both are at the same time at the 0 point. Hence, the result is flat, meaning it looks from the outside like no wave. Huh? Or we have then a superposition in the other way around that it is constructive, so it starts to add up. Quite straightforward, actually. We looked at the example of the loudspeaker where we realized they may be a bit out of sync, so they will always, and we go into that briefly again. So because that is called coherence. And but before we do that, we investigate a bit further about the well, the interference, the superposition. It's basically the same thing. It's just two different words. With then we rather talk about constructive or destructive interference. So we rather do not talk about constructive superposition or destructive superposition. It's not wrong, but it's not just simply usually not used. Huh? And based upon how they superposition itself, this is of course depending on the path difference between the two waves. When they have to, I mean, it's actually comparative kind of simple when you just try to visualize that and say, well, okay, the waves they move forward with the wavelength. So of course, then per second we have a frequency that tells us how many times a wavelength has been made per second, which is nothing else in the end but a distance the wave traveled within that 1 second, for example. Hence, the reverse of that is the respective hertz. Huh? Or, well, the wavelength times how many times it occurred, so we have the distance. And of course, when they arrive at the same point, it's kind of logic, and we see that here already. If they arrive at the same point at the same time, then of course they either add themselves up, like here, simple example here, or better said here actually, this is a bit better, because these are the simple. So you see the result, they just add up, because they're at the same time, here it's very clear, and because they are the same wave, for example, then they add up. Huh? So the displacement is a different story, but the time, and if they are having like that, they must be of the same wavelength, otherwise it won't work, unless of course they have a phase shift. But then you may still have the same wave, but just phase shifted. So we look at the very simple situation. They are in phase, so that's the resultant. And of course, because they're the same, they start to add up. Or if we launch them differently, or let's say the one is a sign, the other one is the opposite, as a minus, for example, then the result is zero. Then we have the destructive superposition, or like we say, the destructive interference. That means they travel the same length. So it at the starting point. And when we look at that, we can say, well, we have the valley and the peak, and if it's adding up, let's make it like that, so like this, and the other one is the same, just make it basically the same. Huh? So obviously the resultant is then just more or less double. Sorry, that was not correct here, of course. Should have gone further down. Like that. Huh? No, well, that's totally out of sync. Let me do that again. Sorry, that's not a good example. I mean, I'm sure you know what I mean, but it just doesn't look right. You have the blue one, which is the super, which is basically the same. So hence we just get double. Huh? Let's say double, double, so something like that. Like this. Huh? So that means they add up. Which we can say, if we look at it now on the distance of what they travel, they will always be at the same position. And in that case, of course, that one travels like that, if that's time, and the other one does exactly the same. So that means at any given time, they're as well at the same situation, position. And as so, it means you always have the multiple of the wavelength actually at the end of the day. So if we say this is the wavelength, then of course you can say, well, wherever they meet, then they always superposition themselves, or they are constructive. So it's a multiple of the path difference. So they may between the two actually, because the path difference you have to look at it in a bit more detail later on, because there's some calculation, not here, that we say, okay, if the path difference between is the multiple, an integer multiple actually, then they will always be constructive. Wherever they are, they will add up. Like what we try to illustrate here, that wherever they are, they always add up. There's no destructive interference ever, because the path difference is the same. So of course it starts with 0. That of course is the most obvious one. But of course they could be phase shifted, and then of course, but they are exactly the same wave, so they have the same wavelength. So doesn't matter. When we see that, we can now show that situation. That was the most simple one, but that's path difference 0. So if you go the other way around and say, well, one goes like that, and let's say is for example, one time the wavelength just starting, then it will be according with the multiple of that one. So what I try to say here is they arrive at the same time at the same place. And henceforth, they are constructive accordingly. So, or always adding up, that also could be as well like this. And when we have this one, then we can see we have a phase shift, so it starts to be destructive because it starts to eliminate it, but they may have an not in phase. So there we have there's up quite a few sub options, but the easiest way is just to think they are in sync. So what happens there is that we say the path difference between the path difference of what the distance the wave travels. Repeat the path difference. And that would be nothing else but 0, 1, 2, 3, 4, 5. So, and with path difference lambda is 2, 3, lambda. So the path difference is always the multiple. Or in other words, we have that path difference delta d is n times lambda. So of course the question is then how do I calculate the path difference? That's something else. We look at that later on. But right now we just take it that they have a path difference of what they travel. And if this is a multiple of that path difference, then they will always add up because they will always hit again at the same spot. But if we go the other way around with destructive, then of course it's, well, halfway through. So they will opposite. That's the easiest way to look at it, which is very clear if you are like that. And of course, if I have this, right, then I always have an offset here at least. Huh? So it's destructive. This one is 0, this is plus still, but it's not just superposition in terms of constructive interference. So in that case, we talk about it's half the path difference. It's even better when we look at the double slit experiments where it's even more obvious of how that really works. And there we say, well, the path difference in that case is not starting at 0. That's obvious because there they meet, but it's half lambda, 1.5 or 3.5. It's a matter of, or then 5.5, etc. So obviously it's 1, 3, 5. Always half, of course. Or we can say 1.5, 2.5, 3.5, 4.5, 5.5. Same thing in the end, but I think this is more like the sequence to be seen. Like here we have the integer 1, 2, 3, and we still have, and then it's with odd and even, whereas here we only have the odd numbers, right? But of course half of it, 1, 3, 5, 7, 9, etc. But half. Or in other words, that's why we can write it down like still n plus half times lambda. Because then we can say n is always 1, 2, 3, 4, 5. So that's the other way around, the way to look at it, which is put that in brackets, and then we can say, well, it's half lambda, 1.5 lambda, 2.5 lambda. So there's an easier link between the two if you write it like that, which is the standard case. Or of course you can look at it as a number sequence in math, algebra, a numeric sequence, and say, well, it's actually 1, 3, 5, 7, 9, so it's just an odd number sequence. Whereas here it's both odd and even. But usually we show it like that we just say n plus half. But that sometimes is a bit misleading, to my opinion, insofar that, or you may just say, well, because in the end, it still goes by 1, if you really look at it, at the delta in between, right? So this one is still the same difference, of course. Same here, it goes from half to 3.5. So it's still 1 lambda difference, but it just starts at a different point. So it's simple as, in that viewpoint, it's nothing else but the valleys and the peaks. So we add up either the peaks, that's here, constructive, or we have the valleys and the peaks. Of course, they eliminate each other. So that's a simplified version to some degree, if you want to say so. So they add themselves like this, or we have the valleys and the peaks, and henceforth they just so eliminate itself, huh? And then of course goes like that. So that we have always the elimination accordingly. Huh? So that the difference is then between still one full difference, but it starts with the half, 0 to infinite. So far so clear, Christopher?
Yeah.
So now a bit, let's say, how we typically get that is just here a very simple illustration that we have a laser, because it's one wavelength, one frequency. We have the double slit, or the slide with the double slit, and then it splits it into multiples. So this is a very, we know that already, kind of. Here it's now just showing the experimental setup, and we see the result. But of course, how the result then really looks like, that's a different question. Huh? That is something we investigate furthermore, and for that purpose we usually do that with the double slit. It's a bit easier to show what's going on. But we continuing with this one. What we have here and is then the coherence of waves, actually, of light. And we encountered that already with the loudspeaker, where we could see in that example they're in and out of phase, not exactly in a random way, of course. You can describe that ultimately with an equation, sure, but we see that it will always be, well, non-coherent. So it's a very simple, straightforward label we give that situation. and say if it's in and out, if it's coherent, that means it's constantly in phase. If it's permanently basically in and out of phase, then we call it non-coherent. It's something to remember. It's pretty obvious, but something to remember, um, that such waves coming from two sources, that they have a constant phase difference. Of course, they're coherent. That's why we then call that a coherent source as well. We can see that a bit illustrated here. We have a phase change. If we want to have a clear interference pattern, like with the double slit experiment with A and B here, because when we have two sources, and you can imagine, when you have two loudspeakers, they come from the same source, say a record player, radio, whatever, amplifier, and then they are left and right positioned. Theoretically, we have the same cable length, maybe yes, maybe no, but more important is how they are positioned compared to you. And of course, if you move in front of the loudspeakers from left to right and so on, but you want, of course, not to have a different sound arriving in your ears. So you have to, and the problem there is related to that, to make sure that the sources are really totally in coherence, right? So that they're coherent. And it could be like what we've seen here with that brief calculation here, that there are no a slight phase difference, meaning a frequency difference. And of course, you won't hear the same sound from left and right, because suddenly the one sounds a bit higher pitched or lower pitched. A terrible music experience. If it's in a very small range, you may not really hear it, but for the, say, hi-fi purists, they really pay high attention. So in that audiophile world, where it has to be as accurate as possible, such kind of things count. For us, let's say for us, so to speak, as regular listeners, we just want to make sure that we do not hear slightly different sound from left and right. And it's not so just coming on its own. It needs a technical solution to make that. Of course, if you have only one loudspeaker, problem solved, but you won't get the stereo effect because our ears are as such that we need to have two sources at least. Ideally, of course, like in real life, it's surround sound. But the two loudspeakers are a good enough approximation to have a decent sound experience. Then they have to be coherent, so that they're in phase. Same word, two words for the same situation. Of course, when we talk about electromagnetic waves, the other ones are ultimately acoustic waves, obviously, to listen. Then, of course, you can solve the problem by using a laser, right? Then, and with a double slit. Then that's another way to achieve that. Then you have the slit, so to speak, as the source of the coherent light source, so to speak. So they're still the same. That's trying to be illustrated here. Incoming wave has a double slit, and then they continue because of the slit effect. There's something happening, but then we have the same wave twice. Instead of having to produce that, when it comes to electromagnetic waves and nothing being turned into an acoustic wave, for example, then of course this is the preferred way to do it in order to get that coherent situation. Now, right now, it's all a bit theoretical. What is the practical application of all that? Right now, it's just important to know that this is one way to sort the basic problem to get a in-phase wave movement or coherent wave movement. Okay, so out of phase, this one non-coherent, this one with a laser to get a coherent. Now, the next level is actually the double slit. The single slit is the basic explanation, so we see a bit what's going on. But the one with the, which is really interesting us ultimately, is the one with the double slit. And of course, with the double slit, I mean, here's the illustration of how it looks like. We see, or let me ask you, what do you see here, Christopher, on that picture here? This is coming from this is basically what is this one, huh? So when we look in this angle, then we see this pattern. And what does that pattern show us?
Like small regions of constructive and the destructive interference.
Okay. Which one is the construct? I mean, it's obvious, but still I ask, what is the constructive interference here what we look at?
The bright parts.
Exactly right. So basically, the lights, as it's from the same source, they eliminate each other. So it's basically black, right? Dark. There's nothing there because they eliminate each other. Exactly. What else can we see here, Christopher, when you look at it?
The intensity decreases as it moves
Yeah,
more
good one.
outwards.
Yes, exactly. So this one is even going into yellow. The others are then getting the brightness becomes less and less. And what else? What is the third observation we can make? When you look at it from inside to the outside, I mean, taking that as the center, and then you look at left and right, what happens to the wave as well? Is it, or in other words, even if it's a bit dark here, does it look like it's, if you really, really, really enlarge it, see, of course, there's probably some pattern from the lens where the picture was made. But what you can see here as well is that it seems that the brightest spot behave a bit like this, huh? So the intensity is really showing like it's just the core, and we ultimately can't even see the core anymore. When we really enlarge it here, there's still something weak, shining kind of, but compared to here very intensive, so intensity, but it seems to go down, right? So the expansion of that one is less and less. So there's something. So we see why that. So that means clearly it's a complex overlay of the various waves, and we want to investigate a bit how that happens. Huh? What's really going on? So for that purpose, we make an simple drawing where we take point A, B, C. Just basically, so A is obviously the one in the center, and we just look at one side. I mean, because it's clearly mirror image. But it needs both slits in order to get the same pattern, of course, on the left side here, as indicated on the picture here. But from an explanation point of view, of course, we only look at one side. Doesn't matter if it's left or right. So in this case, we chose the right side, so to speak. Huh? So the waves come here. So when you look at the point A, B, C, for example, and coming from point 2, what can you say about the three rays originating? Let's call it they originate at point 2. What can you say about these three different waves going to A, to B, to C, as a 2A, 2B, 2C, so to speak? So 2A, so to speak. What could you say about these three rays? Just as a basic observation.
Um, when it goes further away from the normal, it,
Mm-hmm.
it requires more distance.
Exactly. Yeah, good one. Exactly right. That's the real core of the whole thing. Is comparatively straight, and it's straightforward. It's just becoming more complex because many rays happen. But exactly, huh? So they have a longer way to travel, and we know that it's light, so it cannot travel faster. So it's the speed of light, right? That is one of those how it was being identified that there's an ultimate limit for the what we call speed of light actually. Also, of course, it's the limitation for any type of wave. Also electromagnetic waves actually. So what happens? So if the velocity or the speed here it's actually the velocity um, is what happens to the time. And what you said the distance is different, right? Assuming one is longer than the other, but they travel at the same speed. So what will happen at these points here?
takes more time to reach.
Yeah, exactly. Exactly. Of course, we can't see that really, um, that they travel longer, but the experiment reflects that, and that is then the phenomena we see. So we have to go backwards, so to speak, and say, hey, okay, that's what we try now to investigate. If the distance is different, but the speed is given, of course, they have a different timing. So something must happen. And we see that. And now we go backwards and say, okay, why and how does that really happen in the end? So what we have at point A, let's take that. Um, we have, of course, and what we can see as well is that, of course, they arrive from point 1 and from point 2, because of the way of what happens here. Just these three are obviously the ones to illustrate. So this one goes to point A as well, and so does this. So when you look at that, what are these two rays doing?
Um, they're overlapping.
Yeah, exactly. So, or another, is the distance here the same as the distance there?
Yeah.
Exactly. Yeah, exactly. Right, that's obviously important, right? So if the distance is the same, so hence they arrive because we are looking at it's that famous mix between time and distance, right? Which ultimately is kind of the same. It's just basically a different way of looking at it. Do I look at the distance traveled in a certain time, or do I look at the time, hence what distance has been traveled? So that's a bit the overlap what we have here. Look at basically the same thing, but we have to choose sometimes this angle, distance, and sometimes that angle, time. Whereas here they overlap. So the time-space continuum, so to speak, is identical here. At the same time, they travel the same distance. Now, when you look at point B, and you look at this one and that, oops, let's make it a bit bigger. So, and we look at this one and that one. Still true or not with the same distance?
No.
Right, huh? Exactly. And which one tries a bit further? Travels,
Uh,
sorry,
1B.
1B exactly. And so that one has a longer distance than this one. So that means at the same time it will not be there really yet. Of course, with the delay, and that's exactly where the phase shift comes into play. Ultimately, there's always light arriving here, but not the same which originated at the same. They could both arrive at the same time at one because it's one laser beam, which then splits. But of course, then that one, that when we would label that ray, so to speak, which then will arrive at that time, which takes longer. So this one has arrived, and this one is still here. So that's where the phase shift happens. That's why we start to talk about phase shift, because of course the rays constantly arrive. So from that point of view, it's like, oh, what are you talking about? There's always a ray of light coming. Yes, but it's not the one which started at the same time. The journey, the one and the two, have same starting time, but a different arrival time. And henceforth, that one travels in that regards not, well, can't say really faster, but of course sometimes we may say faster because it has a shorter distance. So we are not that precise in our everyday language, right? Has the same distance, has the same speed as this one, excuse me, this one, but because, no, wrong, has a different distance. And that's why we ultimately in that experiment with this equidistance here in the vertical, as a vertical from that angle, horizontal in this, when we look at it from what we just have in front of us, then of course it looks like it traveled faster, but of course it didn't, it just had a shorter distance to travel. And that means that one has not arrived yet, and henceforth we can really go more into the details of now, okay, now we have identified a couple of basic um, properties, now we can start looking into it. And of course for C it's even worse, right? There it's very, very obvious. So basically that's the opposite, the extreme opposite of the equidistance from A, right? So this one is same, and this one is the most extreme one. Longest distance, shortest distance, so to speak. Well, in the situation for C, of course, and to illustrate the extreme situation. Of course, we can go as well the other way around. and look at it for this one and that one. Huh? Just the opposite. Okay. So, and when we now go into the calculation, so we can start to label it. Let's do that and get some basics in place. We have the slit separation, so that's this one. That's A. And so we call that the slit separation. We have the distance between the points. The fringe separation, we call that as well. And it's important because here we see the result. Huh? So bright and bright. The intensity is a different story. We just look at them. It's bright, whereas B clearly is dark. So that means we know it has had them annihilated. They have annihilated each other. So something must have happened. And then when we look back of what we said when there's an annihilation happening, so obviously it's exactly half, and that's what you would expect, right? That's where we talk about the distance here in this part. This one, when we talk about the path difference, right? Then we start to see a link between that, because as a result of that, we have a dark situation. Basically, it's in the middle of between A and B, A and C, and of course, we have two peaks and one valley, kind of. So we have the brightness points, but in the middle, of course, it must be in the middle, the dark spot. And that can only be exactly the half distance, like the n times half lambda. So here we have it, and that's why when we have the A, so let's jot that down, A is our slit separation. And of course, later on, we can play around with this a bit in order to achieve certain effects in respect to, of course, the frequency of the laser, meaning the wavelength of the laser. So there's a certain way to play around kind of between the slit separation and the wavelength. Then the fringe separation, which we call X. And that's important. So fringe means clearly the bright to bright. It's another word to remember. That it could be something else. It could be theoretically that we call this the fringe between bright and dark. Why not? But the way it has emerged, of course, we call bright to bright the fringe, which of course has a link then to our wavelengths as well, and the multiples of it accordingly. And last but not least, of course, we have the screen distance, number D. So that has an impact as well. So basically it goes back to slit to screen. Slit to screen. Screen distance. So from that angle, it's basically geometry, right? Which we apply here, even for something like laser with frequency and certain wavelength, and double slit, and then the bright spot and then the dark spot, which is good news, huh? So we can bring it down to basic geometry at that time, at least. Now, when we now say, okay, how can we now figure out the wavelengths, huh? of the, and when you look at it, it's not further explained here in more detail. We can do it in the double slit. Of course, when you to go into the respective geometry, like I just said, but you may go through that in class, most likely, but you won't have to repeat it per se. So what we can say is when we put the ratio of A to X, so between what is the distance between, sorry, the ratio between the distance between, so the fringe, the length of the fringe, and the width of the fringe and the width of the slit, that ratio put in ratio to the, sorry, no, I have to start again. That's what I was. What I wanted to say is that we have the distance of we can say the slit But of course, it's shown it's basically x to d. That's what counts here in that context. So what is the fringe distance compared to the distance between the two, or the screen distance, or the distance between the double slit and the screen, so to speak, or the nominal pathway of the wave. Huh? So nominal pathway would be this one, basically. If it would go unhindered, so to speak, without the slit, it would just travel through. So what is that reference travel distance, so to speak? And in consequence, then we can say, well, what is then the ratio between the fringe distance? So how does it spread out compared to if you would have traveled? So obviously it starts to go in here, and that, of course, in ratio or multiplied in that context with the A, or you can say as well A in respective to D, as well as X in respective to D. And that is then the wavelength. So when we give the, let me see, we do an example with that one to give you a bit some numbers. And what we get here is to say, well, we have A, you can see that is 1 millimeter. I use that one. We still have to turn it then into meter probably. Then the screen or the slit to distance 2.4, that makes about sense because you need a certain distance, not too far, but we can, that's some, if it's too far or too close, there's some effects, we can discuss that later. And we say the width of 10 fringes. Now, typically when you do the experiment, then it's sometimes a bit difficult. If you just take one or two, there may be a too high uncertainty. But if you kind of average it out by, for example, taking 5 fringes or 10 fringes, then it's less dependent, right? If you just say, oh, okay, I have A, B, C, D, E, like here, for example. So I measured that one to this one. So whereas if I only measure this one to that one, or the uncertainty of the accuracy is a bit too high comparatively, but if I take it for 5 spots in a row and then have then the average out, so in tendency I get the better result, unless you have high precision tools at your hand, right? But quite often we basically just use a meter, a ruler in order to get that. So that's why here we talk about rather 10 fringes, and so 10 fringes. So in consequence, we have 10x, so 10x, and you have 1.5 centimeters. So, I mean, the idea is now not to make it as complicated as possible with millimeter, meter, and centimeter, but that's the reality of how you typically measure it in tendency. So it's more as a side effect to identify that, not as a challenge. And now, of course, we want to calculate the wavelength in nanometers. Because that's what we typically label the lasers. We don't talk about millimeters or meters or centimeters. Typically we say, oh, that laser has a wavelength of so many nanometers. And quite often, because of those slit experiments, you rather talk about the wavelength than the frequency, actually. Of course, could talk as well, but in tendency, you talk rather about the wavelength. So, first of all, we want to know the fringe separation in meters. So of course now first we have to get our units of measurement into a better perspective. So when we say what is now answer the fringe separation in meters, how would that be? Well, how much would that be, Chris? For one fringe, because we only want one. Huh? Right now we measure 10.
The length divided by 10.
Okay, and then put into meter.
Times 10 to the power of, I think, -2, because we measure it in centimeters.
Ah, okay. And now if you go to meters, okay.
Huh?
If we're going to measure it in meters, so how many? What is it then? Which power is it then for if you go for meters? Right now you would have 1.5 times 10 to the power of minus 2 for centimeters, right?
Yeah.
And if you go into meter, then what is the power?
From meter to centimeter?
Mm-hmm.
Power of 2.
Okay, all right. Okay, let me see. Yeah, I mean it's fine. It's just what. Did you incorporate the 10? Because it's 10x, right? So we measured 10 fringes. So but we only want to have one now. From a practical experiment point of view, you would not measure 1x, so from A, B, so A to B, you actually measure, in this example, actually C, D, E, F, G, whatever, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you measure that distance, right? Or you know it's 10 fringes, but you know it's 1.5 centimeters. And you can see from that, because that's of course a real life stuff, that you have 10 fringes within 1.5 centimeters. So if you want to measure the individual one, it becomes no, you probably have one chance. Of course, you can increase the D, that you get the wider spread between the highs and the lows, or the fringe spread is larger if you increase the distance, of course. So you see that within 1.5 centimeters, so that would be about here. You have 10 points, right? That's
Then would
about
that
now.
be
Okay, 1, 2, 3, 4, 5.
divide by 9? Because it's the fringe, the distance between the fringes.
Ah, okay, okay, my bad. Yeah. I mean, I want to say you have 10 fringes. Huh? Also 10 fringe distances. Sorry, the phrasing was not correct. So, yes, it's 10 fringes and not 10 points. So I forgot the K. Yep. In that regard. Huh? So it's 10 fringes, so 10 times x. Huh? 10 times x. Huh? So that is only 1.5 centimeters. So it becomes really difficult to measure that here, right? So it's even that is already enlarged. So if I can't make it less, well, I can. So that's about. I mean, of course, it depends on how it's projected on your screen, but this is about 1.5 centimeters, roughly having 10 x's, roughly like this. And so if you want to now measure one, it becomes really difficult. That's why you rather measure 10 and divide it by 10 in order to get your number. So that's why it's here with the 1.5 centimeters for 10 x's. Instead of 1x is 1.5. So it's not a complication to make our life a bit more difficult. It's because the experiment well, if you would have to repeat it, you would do it along the same line. So henceforth now, what is the power of x, or what is the dimension of 1x when you go for meter, or the value of x in meter?
-3.
Yeah, exactly. Okay, right. So we have our x, huh? And now if you just look and say, well, what do we want? We want AXD, huh? AXD. So of course now we have to do the same. This one here was just from 10 to 1. Otherwise, of course, we have to do the same for millimeters, but this we can do. So what is A? The value for A?
1
For the
times
1
10
millimeter?
to power -3.
Okay, yep. Then we have done this 1.5 times 10 to the -3. And we have 2.4. Huh? So what you can see here is that actually there's a certain interesting part here for the A and the X. Huh? So what is the distance? So we can see that this one, that's why there's a certain kind of a ratio in it here as well, even if it's multiplied. But you can see, or you can say it's then a multiplier a ratio effect, that you say, okay, if that would be the same as this one, an A1 in that case. Of course, it multiplies as well, but it increases. But if the ratio between what you want to achieve with the slit distance and the fringe distance, as of course the impact is related to the wavelength. So you have really, when you design the experiment, you have to be a bit careful in that regards which laser you choose. Of course, usually you don't have so much choices, that's cool. But say in a lab with infinite possibilities of available lasers, you would then really have to think about how you set up the parameters in values here, together with the wavelength, in order to get the best possible experiment. This is a bit an indicator here. We don't really explicitly do it here, but you can see a bit the values, how they are together with each other related. And of course the distance then obviously cuts down the wavelength, of course. Makes a lot of sense anyway, right? The further away you are, of course, the wavelength must be accordingly then less, because the frequency must be higher. Okay, so when we look at that, then we get about 6.25 times 10 to the power of -7 meters. And do you remember what 1 nanometer is in meters?
-9.
-9, huh? So how many nanometers do we get?
Uh, 625.
Yeah, exactly. Yep, exactly. So the question is, does it go up or does it go down, right? So to speak, with -7, -9. Yep. So you increase it by factor 100, and then you get the nanometers here. Yep. Okay. So this is a 625 nanometer laser, and of course, with the wavelength comes a color, because we know that obviously the laser then have different colors depending on the frequency wavelength, and that one is a helium neon laser. Of course, we don't need to know that, but or remember that just to say. So this is highly related to what you are using. The gases could be an argon laser, for example. So it depends on what type of gas you have, which is then in consequence giving a certain light. There's a certain link in that regards. Okay, so if we now move the we use the same laser, but we make a larger distance. That is a typical question. Sometimes you just have to answer it qualitatively, but we here call it. So we move the screen from 2.4, make life easier, to 4.8 meters. And what is that? And the rest is the same. I mean, we have the same slit. So we do not change the setup of the experiment further. We use the same laser. We use the same slit separation, but we increase the distance. So what will happen to the fringe separation? So what is the new fringe separation value now? And to make so just say we say AX over D. So and now we do basically 2D. So with the new value, we make it 2D. So what will happen to the X?
It will also double.
Exactly. So because of that ratio here, it will go actually over there. Exactly. So that's the beauty. So that's why the typical question is if you have a limited space available, well, in other words, maximize the distance, or D helps a great deal to get a higher X, which makes your accuracy better. That would be a typical way of phrasing then a question, for example, to say when you have such an experiment, so you obviously have to measure 10 X's, because 10 X's are already only or still only 1.5 centimeters apart, which makes it near impossible to measure a single X. So that's why you said, okay, let's measure 10. But of course, you can increase that accuracy by, as we just saw, by doubling the slit. We double the X, so we get at least 3 centimeters. Of course, we can then play around with the laser, but maybe the laser is only the one and only we have available. Of course, the question is then, what about the slit? Huh? So if you change the slit size, what would happen? Would you have to rather go up or down with the slit size to get a better fringe, also the higher fringe distance?
Less slit separation.
Exactly right. And then of less slit, so we go, the slit goes down, our X goes up. Then of course it becomes a question of the wavelength, if that's still okay or not in regards to the wavelength compared to the slit distance, right? Then there's probably a certain crash at some point when we look at this one and this one. Huh? So that the laser will not work. The typical thing, right? If it's too big, it won't go through, actually, like what we've seen before. In the just water, for example, it showed that already. Huh? Okay. And so that's a very typical one. And there's one later on. Yeah, we are coming to that one now, where we make where we link the wavelength with the diffraction. So that's that's the next point, because we can say, okay, when I have the two double slit, that's one thing, but maybe I can see something different if I have many slits, which is more real, because in reality, of course, CDs are not so popular anymore. But typically, when you have a CD-ROM or a music CD, Blu-rays usually are coated, quite often coated, I think on both sides, maybe. Then you see when you hold them in the light, right? They have this reflection stuff on it, basically nearly like rainbow, partially. And of course, that means there must be something going on in diffraction, otherwise you wouldn't get that effect. So it obviously splits the light because we only have natural light around us, yet we see various colors on an otherwise silvery or nearly white surface reflected. And the question is, okay, as we know the double slit, so maybe the surface acts as a multiple double slit, so to speak. That's exactly what we look at it next. We call that grating, which is nothing else but, well, many slits actually, but we call that grating, or in that context then diffraction grating instead of the diffraction slit, called the diffraction double slit. And then of course we have then still to look at one and then the overlapping of many. That makes a bit difficult. And what really happens here is this situation. And we have then again the maxima on the screen. So we have maximums on the screen. So, of course, henceforth, as we only have in the double slit, well, this situation which we encountered and calculated and looked at it, which of course already gives quite some complex situation. Now, if we think that we have and again slit and slit and slit and slit, so that starts to repeat each other, and then the overlays start to repeat. So obviously we have quite a situation of what's going to happen. And what we can see in the end is that we have this, when we say N0, like what we said before, there's no change. So we start to link it with the wavelength with the angle, and of course with what we call the order. When we say what is happening in the various situations, where we see various maxima. So the first maxima, the second maxima. There we have to be a bit careful that we say, well, the first maxima is where n is 0. That comes back to our original situation where we say, well, it's a multiple of the path difference. So where we say the path difference is n times lambda, right? This one. So the path difference is here. That expresses itself as the path difference ultimately. And obviously, when we said it's multiples because we have the bright, 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 bright. So, okay, we have a constructive interference. That's what we look at it. Of course, the destructive interference will be at half. That will be here. That's why there is exactly the dark spot. But of course, the distance is still the same. So the distance between the bright and the dark is the same. That's sometimes something students start to forget. That doesn't change. Huh? So the n plus half or the n does not change the distance between dark and bright and bright. It's of course exactly the same for the same laser. It's just that you start with a different point and say, well, first I move half and then I start to repeat the pattern. Makes perfect sense. Or I start where the bright spot is and go from bright to bright to bright to bright. Or I go to the black spot or the dark spot, which is of course on halfway between the brights, hence half, and then it starts to repeat itself. So the distance is always the same. Like we expect from a wave, of course, right? The distance between two peaks or two valleys is the same. So nothing has changed in that regards. But our focus changes. Are we looking at the peak or the valley? And here we look at the peaks, the bright spots, and we start the numbering at 0 because it's not, when we look at it, there's no path difference for the first occurrence. That's what we have here. Sorry for this one, right? Same path. And that's why there's no path difference. That's why we start at 0. That's why we take type n equals 0 times lambda. Of course, we get 0. And so that's the background why we call that n equals 0. So we have, but of course, from a numbering, we call that the first maxima. Makes, on the other hand, sense as well, right? So that's the first max. Because that's what it is, but it's where n is 0. So if you don't have the, I'm sure you have it, but if you would not have the basic understanding what is really going on, then there's endless confusion. Why is the first max at where n is 0? It's basically the wrong question, right? Because we can explain that when there's no path difference, the two waves hit with the same distance, hence they have a constructive interference. That's why we have the first maxima. But of course, there was no path difference because they traveled the same distance, coming from slit 1 and slit 2. So also opening 1 and opening 2 traveled the same distance, hence they arrive at the same time, hence they are in phase, hence they construct, hence there's a maxima. And of course, because it's the one in the middle, we call it the first maxima. So that's basically the background. To keep that in mind. Once it's clear, it's really clear. And then, of course, we can as well, having that basically, it's basically you think about a screen, so to speak, because we want to hit it at the same. So the reason why we show it like that is, of course, we are not having a straight screen in this context, so that we can have the same intensity. And that's doesn't really matter here, but it's a slight explanation, huh? Because you could not, because we have a ray which has the same length. So that's why, of course, we get a circle. Whereas in this experiment here, we have a screen which is straight parallel, so to speak, or in 90-degree angle to the light. As it's here, of course, the rays have the same length. It's like r, the radius of the circle, or of course of the sphere ultimately in a 360, if we would do it like that with a pulsating laser in 360 dimension. And then of course the ray is the same as of length when it hits the screen or the imaginary sphere, and hence we can start to talk about an angle. That's very important as well to remember that. Otherwise the angle makes no sense. Not really, actually. It makes more sense when we look at it like that. Okay, so what we have as a result, now of course there's some calculation involved. We can say now, when you have n, so this is my n times lambda, because that comes from this one where we say n times lambda is my path difference, which is actually the x. So this, of course, I can say now, if I look at it from a geometrical point of view with cos and sine, so what is that equal to, Chris, when you think of this situation now. And you want to put the angle theta into play as well. By taking d, of course, I mean that's into d as still the distance between the slit and the screen. But of course here it's an r also, but we still call it d because we call about the distance from the slit to the screen. But from our viewpoint, it's of course more like a radius in the end. But not to confuse it suddenly that this is the diameter, and just to be sure about that.
Sine.
Yeah, exactly. So d sine theta. So again, just another part of geometry where we can link it easily, where we say, okay, actually here now, of course, it has to be very, very small, otherwise it starts to be bent here, right? So we assume it's still straight, which makes sense because we talk about these max and min in very short distances. So it's okay to make it like that. So and then this is what we call, well, it has actually no real name. It's just to determine the wavelength with the diffraction grating. So the grating is actually the angle in which the rays are creating the pattern of the incident light of the max. So max 1, first max, first, second, third. So that means the angle between from one max to the next. This is what we call that. So you can as well call it the diffraction angle sometimes, eventually, or the angle of the diffraction grating. It varies a bit of how it's labeled. Okay, and what we can as well, we can have two situations depending on how the ray comes onto the grating, of course. But that's not so important. It's just here, or in other words, what you could imagine. That's maybe an interesting point is that these are our eyes. Huh? So this is our eyes when the light comes in, and then it has the grating in between. Then they are all come together, and that's how. When you think of it that there's something off, that's why if all is in order, like they arrive at the same place at the same time, then you see everything in focus, so to speak, right? They're all here, max, 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 in the various positions. But if something here in that system, here we only have one screen, of course, but it's slightly distorted, it will not be like that. So then imagine like it can be slightly out of focus, because they're not happening exactly anymore, these spots. So these spots are slightly shifted, and that is then like not clear picture, so to speak. It's a bit of simplification, but you can see a bit of what may happen if we talk about non-optical, I mean, no focus for the optical eye and then the nerve into the brain to form the picture. Huh? Because the signal is coming a bit at a different time, and hence it will be as well. So it's not just the optical part, it's then the processing of the data into form a picture out of it. But as the information is already distorted, of course, the brain can only adjust it or not, or process what it gets. So theoretically, you could say I can have either a lens which corrects that, or I could go into the brain and correct it there. So I think the lens is probably preferable instead of messing in the section of where the brain forms the ultimate picture and corrects the incoming data, so to speak. It's better to do the optical adjustment instead of the later on, so to speak. Huh? But that's of course always on the table these days with all the artificial intelligence and whatever else and enhancements of our brains and limbs and muscles, etc. Okay. So here is just indicated if there's like what we see here, right, in B. They are in they have traveled a slightly different. It depends on how it comes in. Though each one of them has, of course, traveled a different distance, right? So they have traveled the same distance. So the effect of the distortion can be as well something like indicated here. Huh? Okay, then let's make an example. Give it some flash. So we have monochromatic light, as it should be, as a laser. Monochromatic light. And it has a diffraction grating, now comes this one, of 300 lines, so 300 lines or slits per millimeter, huh? Per millimeter. So it's very finely grated. Actually, everyday language used for this physical situation. Huh? So we have 300 lights per millimeter. So that means we have 300. These are the slits, so one double slit, like you said before. Like so, we have the slit in between. So there's one. And then there's another one. So with 3 lines you have 2 slits, huh? The normal fence and pole probe. Okay, so that creates the quite something already as an effect. And then the angle theta between 0 and first order maxima, also between the maxima is like 10 degrees, so theta is 10 degrees between maxima. And now, of course, we want to know the wavelength.
Wavelength. So 100. No. 1 divided by 300.
Okay. Yep.
No, 1 times 10 to the power negative 3 divided by 300.
Yep. 1
times sine 1, sine 10.
1 times 10 to the power of minus 3 divided by 300, right? Okay, so and then so we have is yup, sine 10 degrees, huh?
Yeah. And then all of it divided by 1.
Okay, yeah, because we go by n, huh? All right. So, and then we get they made a typo here. Sorry, it's 3000. That doesn't really matter. Okay. Okay. Yep. Otherwise, the laser makes no sense. So what do we get, Chris?
Wait, I need.
Yeah, it's good. Or I can say 3 divided, so it's basically sine of 10. It's quite small. Because it's divided by 1, if you want to say so. Divided by 1, everything divided by 1.
5.79 times 10 to the power negative 8 meters.
10 to the power of, and you get
negative 8.
negative 8. Let me see. 1 divided by 8. Let me see. They make somehow a mess here, actually. Sorry. So if you have 1 millimeter, 10 to the power of -3, no? Times divided by 3000, yup. So we should get that. 0.01 divided by 3000. So Chris, how much did you get for the 10 to the power of -3 divided by 3000?
3.33 times 10 to the power -7.
Yep, got the same. Okay, so that's fine because I just look at. Okay, that's fine, but something is not correct here. Well, let's go back. And if you let's take the 300 again. Sorry, make it into 300. What do you get then? Yeah, okay, now. Okay. Now we okay, it's 300 still, so they were flip-flopping back with the typo actually. So okay, so here we go. Still 300 lines, huh? So what do you get now with 300 lines per millimeter, Chris? Do you have it?
5.79 times 10 to the power -7.
Exactly. That's why I was puzzled that can't be with the -8. But of course, you were right with the numbers you had. So that's why the 300 is still correct. Because I saw suddenly they changed to 3000. Because what you get if you now go into nanometers, how many nanometers is that?
579.
Yeah, exactly. Yeah, that's why, because the other one would make no sense for a laser. Okay, so we have a 579 nanometer laser actually for the wavelength, huh? Because we're talking about laser being in the experiment. Huh? Okay, all right. So I mean, nothing really for the calculation point. It's quite straightforward. It's not so complicated actually, the equations here, but it's more the basic understanding. So that's why you will always encounter some basic calculation, but some additional questions for the interpretation. Huh? And let me see. So when we okay, that's a bit on the easy side. Let me see. Okay, because of the sign, that's why it's a bit different. We had the five. Let's make it 580 nanometers, right? Let's call it 580 nanometer. And when we get when we get the next maximum, the second order maximum. They have a bit of strange way of phrasing that right now. Or maybe, okay, Chris, I have to make one correction. You can cross-check that with your teacher when you go through the material yourself, because I realize here they talk about the first, what I call the first order maximum, they call the zero order maximum. So,
Oh,
so, so n is 0, they call it the 0, but that's a bit odd to me, but maybe they changed it here for the textbook. So better cross-check, but the normal, no, I can't say the normal way, the way I'm used to be, to have it, or used to have, at least, yeah, even with other students actually, but that was not
in the
first
equation,
maximum.
uh, in the equation, don't they use like the number of order? So if we use it like 0 is 1 and then 1 is 2, then wouldn't that make the calculation wrong?
No, I know what you mean. No, no, you have to distinguish in that case between what is n and what is the max. So because in what I just said, let's put it here. Okay, I do it in red. N is 0. Let me eliminate that. So we go in here. Huh? So when we say n is 0, if you look at it from the max point of view, this is the first maximum appearing, right? So the logic in what we used to have was to say, well, this is the first maximum, unrelated to the n. No link to the n per se. So the numbering is not the same. Where my n is 0, I have my first max. Because the two rays are in phase, there's no phase, no difference in path. And that happened, and of course, hence it's n times wavelength. There's the distance is 0 because it's the same, the waves have the same path, so hence there's no path difference. So that's where n is 0. You can as well say, as we said, x is n times the wavelength. So in this case, it's 0 because that's what it is, or the x then. But we call that the first max, and in that logic, we call that the second and the third. And the same, of course, because it's symmetrical, we still call that the second and the third, just left and right. There's no difference, like here actually, minus and plus. But of course, what I see now, right now in the book, they say where n is n, they call it the zeroth max, and that's the first, and that's the second. Huh? You see the logic, Chris?
Yeah.
So here they link the n with the number of the max. There's a logic on its own, which is fine, of course. It's just a matter of what do you agree upon. And until what I always used, because it was like that, but here it's a bit different, that we just said, okay, where is the first maximum occurring? That's where n is 0 for the explained reasons, and we call that the first max because it's the first max. It's a bit odd to call it the 0th max. But of course, if you link it to n equals 0, it has its logic then on its own to call it the 0th max. It's just from a physics point of view, not math-wise, physics-wise, you would rather call it the first max because, well, that's the first max you see. And if you go back to the appearance in the lab here, then of course that's where you see the first maximum. Only after you identified the logic behind with the math included, n times lambda, that you can call it the 0. But from a appearance physics point of view or experimental physics point of view, of course, I mean, I have to make it right. Of course, you call that the first max because it's the first you see, right? And hence, this would be then the second, and this one the second as well. Because you go by what you see. Physics comes in that regards from the experimental path. Of course, it has to be linked with theoretical physics and math physics. So just to make you aware, huh? So not that you think, okay, what was I told? So probably you go this way, probably, huh? And not that one, but that's something you will see in the lesson then of what the teacher is using. It makes no difference, but when they ask for the first max, but their logic is 0, 1, 2, then of course you better be careful. And that's exactly the point here with that question now, because the question they say, what is the first max? So in my case, that would be the second max. Huh? So finished with all that and say, if I now go to the second order max, then of course I know what they're talking about. Then I know this is the 0, this is the first, and this is the second. Huh? This is the first, and this is the second, because n0, n1, n2. And this is 10 degrees. So what is the angle for the second order maximum? Is theta still 10 or what is it?
Needs needs to recalculate.
Okay, so, all right, and let's do that. We can do that here. So of course my basic is still the same. So I just write it down once more. Huh? So d sine theta is equal to n times my lambda. Huh? And of course I want to know my theta, so or the sine or the minus sign doesn't matter. So sine theta. I mean straightforward. Then invert the then so what are the values now involved? When I talk about the second order with the logic order equals n.
2 times the wavelength.
Okay. Yup. 10 to the power of 9. Minus 9, I mean, sorry.
Oh.
And then, and d?
Negative 6.
Negative 6, huh? Exactly. So we have something like resulting minus 3 and 1000 divided by 3. So we still have something like 350 probably. So 0.3. So we get 0.348. Huh? So what sign is that? And what degree is that? Sorry, that's the sign. So what is the theta now?
20.37.
Okay, huh? All right. Okay, so what do we see when you compare? So that would be 2, huh? And now this is theta 1 was 10 degrees. N by 1, n equals 2. So and you is it why is it the angle increasing?
Because it's further away from the center.
Yeah, exactly right. So exactly. So that is expressed with n. So it's quite elegant somehow and easy if you think about it. So it will, of course, the path is increased. Henceforth, it will start to change. So I mean, I'm not going into the further calculation, but what would you expect of how many maxima can you see roughly?
We need to, because it cannot exceed 90 degrees to the side.
Okay, yeah, exactly. Yeah, all right. So max, so theta is a max, or we can as well say like what you just said. Theta has to be less than 90 degrees, most likely. Oh, exactly. So that gives us a certain limitations. Of course, we can start going through the numbers because obviously if you theta 3 just give you the value is 31.5, theta 4 is 44.2, so there's a certain growth in it as obviously in it. So yeah, I mean we would have to calculate it and go there through. We don't do it. So but in the end there are 11 maxima, huh? So 11 maxima. Which means if we, and that's why, of course, the n is easy to say, but of course, so you have the one in the center and 10 to the left. No? So that's why when you think about it here, that you have a less than as a 10 degrees, but it's the distance will be modified. So this one goes from 10 and then plus 10.4 plus another 10, 11 because it was 10.4, right? Then it goes here to 31, so the distance is now 10.2 roughly. So it's basically 1, 2, 3, 4, 5 roughly, in an approximation. That's how the angle grows. So that's why we have a limitation of how many we can have then, apart from what you just said, of course. But okay, so we have 11 maxima. Huh? Okay. I mean, not to remember, but it gives us an idea when there's such questions are coming. So we cannot see more, period. Because if somebody says, you can see infinite maxima, that would be a typical question, right? Explain why student A is wrong with his statement, for example, in the most easiest way. Then you can say, well, because of the angle and stuff like that. That's why. We have a limited number of maxima. You don't need to know necessarily which number, of course, but there's a limited number because it goes by the sign. Exactly. And okay, we can have, as I say, these questions are more about basic explanations, more qualitative than quantitative, actually. So we still look at the same, but of course, sine theta is n times lambda. And now, how does the pattern change when the wavelength is increased? So wavelength goes up. We leave the same grating, huh? But the wavelength is increased. What happens? So n is, of course, 0, 1, 2, 3, no change. Lambda is increased. Yes, lambda is increased, sorry, the wavelength. D, what is with D?
D has to be constant.
Okay. So what is the remaining basic relationship when we think of n and d are constant? I mean, yes, n is increasing, but if you look at the same situation for a specific n, and d, like you said as well, grating, right? We leave the grating unchanged. So what is the basic relationship remaining in the equation?
I think that because we can use the angle as the max angle as 90 degrees.
Can. What I wanted to drive at, Chris, was to say if I have these two as constants, right? Because they are the same, so it's same situation, A and B. I only changed, sorry, this one, of course, N and T. So I only changed this one. So what I can go to is to say, well, in that case, the sine theta is proportional to or the other way around, of course, proportional to my lambda, because the others are constant. So I can take them out. I mean, mentally, visually helps as well. And if I look at it like that and say, okay, if lambda is proportional, and of course to the sign, but I leave it like that because I'm interested in the result. So typically I list that first. So if I now increase this one, what happens to the sine of theta?
Also increases.
Increases, and hence what happens to theta?
Also increases.
Exactly. Huh? Exactly. So from that simple math, you can it's one way to explain it, right? To say, well, if that wavelength goes up, the theta goes up, but you can look at it more from the kind of physical way with the geometry and say, well, if the wavelength goes up, meaning it becomes longer, then when I think of coming to the slit, in that regard, it's still just a slit actually, or double slit, because it doesn't matter if it's multiples. I just have multiple occurrences, obviously, with n 0, 1, 2, 3, 4, 5, with the same intensity, but a limited number of them. then I can say, okay, then I must have a wider spread, which makes sense. A longer wavelength leads to a wider spread. That's another way of looking at it, huh?
Right.
And when we make another one, would be to say B. We take blue light. Okay, blue light, and we take red light. Huh? Also two separate experiments. One with blue, one with red, and we can see that the fringes are closer for blue. So the fringes are closer for the blue one compared to the red light.
Uh, Blue light because it has shorter wavelength.
Okay, good. So in Hainsworth, we can go but in this case, we could. That's good explanation. I like what you said. Is we can say, okay, basically I go back again to my sine, same thing. Oops, that should be theta, not all. Sine theta proportional to 1 over d. So 1 over d. Because I have obviously a change in wavelength, and henceforth I can use that one as well. Okay, so there's more than one way to look at it. I think, as I say, there's not many more calculations. Then we just covered the last one for today, is the diffraction of white light. Maybe, can you explain to me? Actually, we are already over time, but I would like to close that quickly nevertheless. So what is then white light, and what when we see the colors of the rainbow? What would be an explanation in light of what we just in light is good in light of what we talked to this today? How can I utilize that and explain now my situation?
Uh, because the violet light has shorter wavelength, so
Okay.
uh, when it with a constructively interfere, it's closer
Mm-hmm.
to the center,
Good one. Yeah.
and
Okay.
red is longer, so it's further away.
Okay. All right. So the wavelength, huh? A good one. So the wavelengths are the ones. So shorter or longer. Shorter, longer. Exactly. No? And what we call that, by the way, just is the diffraction of white light. Huh? So in that sense, it's exactly nothing else. We just looked at it a bit different in the past. We didn't really explain. We had some first explanations when we looked at the prism, right? When it has the different distances to travel. So now here we go. We are obviously not using prisms in an advanced situation. We're using the grating or the double slit, single slit, double slit, and ultimately the grating, and then we get exactly the same effect. So it's like a prism in a prism in a well, basically with through the slits, not a three-dimensional or two-dimensional situation. Okay, all right. So today was a lot of that theory. There's no a couple of questions we can still follow up next time, and then we already go into stationary waves, huh?
Yeah.
All right. Okay. Then see you next Friday, Chris, and have a good week, huh?
See you. You too.
Thank you. Bye.
shit.